So today I'm going to present a topic about the data attribution for image generation. And specifically, we will focus on the diffusion models. Sorry. And here are the 5 papers I'm going to cover today. So actually, this 4th paper is about the diffusion model. And for the 5th paper, they have a very related idea about the 4th paper. So I also include this one. And this is today's roadmap. And so first, diffusion models usually train on very large-scale datasets, and we all know that it can help us to generate some novel new images of remarkable quality and diversity. However, there are some concerns that some generative models might be just copying from the trained data set. For example, like this figure here, these generated images are just identical with the examples in the trained data sets. So in this case, there are some concerns of the privacy risk and the copyright issues. Therefore, we need the data attribution methods to help us identify the most influential training images that cause the generation of the synthesized image. So although we've extensively studied the data attribution in the context of discriminative tasks like classification and regression, the data attribution for generative setting might pose some new challenges. So generally, we will focus on 3 key questions here. So first, what are we going to attribute in the image generation task? Like, how can we formally define the targets we want to attribute? So today, I think the existing literature actually most focus on the image level attribution, but there are some discussions for like some local properties. For example, we might not interested in the entire image. We might more interested in like how the appearance of object or the styles in the image, which training examples will specifically responsible for this. Or more globally, some paper raised some discussions about the attributing the generative overall distribution, which might be useful for some downstream tasks like detecting the social bias within the trained data sets. So these are some concepts. And secondly, when choosing the specific data attribution methods or developing some data attribution methods, I think for diffusion model, the computational challenge still exists because diffusion models are probabilistic models, involve multiple stages, and often train on very large-scale data sets. So in the context of the image generation, we are going to discuss some retraining free methods like influence functions and also some methods based on the continual training. And finally, in previous session, we've covered some standard evaluation methods for data attribution, like the counterfactual evaluation and linear data modeling score. However, these methods involve resampling and also training the model from scratch, which can limit some evaluation on large-scale data sets, which can be used in the training of diffusion model. So we will also cover one kind of new evaluation method here called customized model benchmark in today's discussion. Yeah, so this is the overall contents. And before I go into the specific methods, I want to do a very quick recap about the basic concepts and notation in diffusion model. So we will focus on the DDPM models, which serve as the foundation of the stable diffusion models. So in the diffusion model, given an initial image, which can sample from some real data distribution and a variance schedule, a forward diffusion process is defined as a Markov chain that gradually add the Gaussian noise to the data according to this variance schedule. Which can be formulated like this. And a notable properties of the diffusion model is that for any arbitrary time step t, the latent variable xt can be sampled directly from the initial image based on a closed form. And then diffusion model parameterize the data distribution like this. So that's something we're going to learn. And when when the variance schedule are small enough, the reverse diffusion process can also be modeled by some Gaussian conditions. And we can parameterize the specific the mean and variance here. And then the model will be trained by optimizing the variational bound on the negative log likelihood function. And in the context of DDPM, actually they did not they set the variance term as an untrained parameter. They only want to parameterize the mean. And instead of directly predicting the data, they propose to predict the noise with this reparameterization. And then finally, this loss function can be derived as this formula. And to better leverage the sample quality, they actually finally trained on a simplified training objective. So this is the formula. And basically, in the training process, based on the simplified training objective, they will sample the images from the training data sets and also sample the time step and the noise and do the gradient descent for the model training. And then in the sampling process, the model will begin with some random noise and sampled step by step, and finally to get the newly generated images. So this is some basics for the diffusion model. Okay. And so our first methods I'm going to talk about today is the journey track. We first will go over 2 papers applying the track methods on diffusion model. And this one is actually proposed by the same group behind the track paper. So given the multi-step nature of the diffusion model, this paper proposed to attribute the generated image step by step. So specifically, their target is to attribute the distribution of the image conditioned on some intermediate latent at the step. So this means that for each step, the training samples will get 1 score based on the attribution, given a specific test sample. And they claim that there are some benefits for this type of stage-wise attribution. First, it will help to do some fine-grained analysis, which means that actually by attribute the image step by step, we can trace the whole trajectory of the reverse diffusion process of the generation process. And we can see that at some earlier stage in this figure, their example. So at some earlier stage, the positive samples might not quite resemble the final sample. But in some later stage, as this process gradually narrow down the conditional distribution of the generated image, the positive sample and negative sample will all resemble to the final image, but focus on probably different features and aspect. So this helps us to get a more fine-grained understanding of the data attribution for diffusion model. And the other benefits they claim is that it might be helpful for some future level attribution. So I think this idea is interesting, but I think there are no much theoretical justification for this one. So empirically, they have observation is that they think the specific feature in the final generated image might actually appear in some specific period during the generation process. For example, here they count the so in this figure, the x-axis is the steps for image generation, and the y-axis is they count the number of image that contains a horse during the generated process. And we can see there a very sharp transition here, which means that the object feature might appear during this process. So if we do some stepwise attribution, it might help us to identify the training images that are responsible for specific features. But actually, I think this phenomena could be more strictly examined for diffusion models. So actually, based on this context, the methods is quite straightforward. So their target is to attribute the distribution, the conditional distribution. And specifically, I think maybe for better implementation, they approximate this target by this formula. So actually, if we get the image for the T step, we can directly use the closed form we mentioned above to derive an approximation of the final image. And this approximation is only based on the information up until the T step. And then we can directly insert this term into the simplified training objective and calculate this reconstruction loss. So they set this as the model output function for the test samples in the track methods. And their algorithm could be very straightforward. So basically, I think most of things is is identical with the check methods. So for the training data points, they directly use the loss function as the model output function, and then they calculate the gradient of the loss function and do the random matrix projection. And then for each step, they apply the model output function we've just introduced and calculate the final data attribution score based on the check methods. So this is a very straightforward extension of check methods on diffusion models based on the stepwise idea. And these are their experiment results. So I think the main takeaway is actually the check methods can outperform some simple retrieval-based methods. So these methods are just based on the similarity score of some predefined feature space or just the pixel space. And then, and both for LDS and the counterfactual evaluation, they observe the same results. Is there any question for the journey track methods? Okay, then I will proceed to the second paper. And the second paper actually is still apply the track methods on diffusion model, but I think they propose some very interesting finding. So in the second paper, their main conclusion is a counterintuitive observation.
Yeah, so sorry, I actually have a one question, which is regarding their evaluation. So when they are calculating this kind of LDS score, so they basically also kind of remove part of the training data point and train another diffusion model, and then yeah, so that's how they calculate the. But how is the yeah, I'm thinking, how is the ground truth for different step calculated? So that
I think for LDS, they just use they just calculate the loss function we've mentioned, and for each model, they initialize the generation process with the same seed. Yeah, and there are some observations that if we initialize with the same seed, the image might be quite similar. So based on this observation, they just I think they just use the same noise and calculate the loss function for different models. Yeah.
yeah, thanks.
Yeah, and for the second paper, they also applied the check methods, and their main conclusion is a kind of counterintuitive observation. So they find that if actually this specifically theoretical justified design refers to the choice of model output function when computing the check methods. So they find that if they use an alternative function to calculate the check methods, the evaluation results can empirically outperform the previous baselines, including check itself, in terms of the linear data modeling score and the counterfactual evaluation. So in the D-check method, their attribution target is a bit different from the journey check. They are not doing some stepwise attribution. They just want to attribute the final generated image. And in the context of DDPM, we can simply set the model output function as the loss function. And we can insert the final generated image here to calculate the loss function. And given this formula in the LDS score, we can just insert this model output function here. And so for different training model, actually, we can use the same, like they just use the kind of same pixel value for the final generated model to calculate this model output function. And the trick here is if in the data attribution method, specifically check. So in the original check, this is the formula for the original check methods. And in the context of diffusion model, they just use the simplified training objective here to calculate the gradient. And they raise the question is, if we change this function here to some alternative functions, will that affect the LDS evaluation results? So I want to emphasize here in the LDS, they still use this simple loss, but actually when calculating the check, this is the method they propose. First, they eliminate this weight term, and then when calculating the gradient, they try different alternative functions here. And surprisingly, by doing this very simple replacement, they find that D-check actually empirically outperform the check methods by a very large margin in terms of linear data modeling score. So here the check methods, this is the check methods that attribute the final image, and this is the check methods. And we can see there's a very large improvement on the LDS score. And specifically, they actually compare the score, the score calculated by like different number of the time steps. So in the calculation of the loss function, we should actually sample the time step and also sample the noise. And they empirically find that increasing the number of the time step will be very helpful to increase the final performance, but increasing the number of the sampling of the Gaussian noise, it won't be a lot of change. So they fix sample one standard Gaussian noise, but compared different numbers of the time step. But basically, we can see using some norm-based loss function instead of the original simple function, there are some large improvements. And to provide some kind of explanation for this type of phenomena, we can examine the gradient of different loss function. So and they propose a deduction there. They think in the simple loss function, when taking the gradient, they're actually this subjection, the original noise might cancel out some information so some information might be canceled out in this term, but for the norm-based function, the information of the gradient might be better retained. So they did another experiment to examine this phenomena. They designed the loss function as the interpolation of the square norm function and the simple loss function. And they find that when the eta equals to 0.5, which actually in this case, this term will proportional to the gradient of the original simplified loss function, the LDS will get the worst performance. But when the eta escapes this 0.5, the performance will increase. And when it goes to 0.1, it will get better performance. So I think here, probably, so they somehow provide some explanation for this phenomena, but there's still a lot of space to strictly justify why this will happen. And probably there are some benefits to use some norm-based loss function in the influence function-based methods. And then these are some results about the counterfactual evaluation. They basically observe the same results that D-check methods. So here, the D-check method actually just use the square norm function. You will consistently outperform the check methods. And also, they did some interesting ablation study I just want to quickly mention here. So in this figure, they examined how the number of checkpoints, how the selection of checkpoints will affect their evaluation results. And they find that if we use the D-check, also the square norm loss here, D-check methods, as the epochs increase, actually the LDS score will gradually increase. But for the check methods, the best performance will not always appear in the last checkpoints. And then they also do a more thorough comparison regarding different methods. So in this table, they first use different loss function as the model output function to calculate the linear data modeling score. And then they use different loss function to calculate the check data attribution score. And they find that if we change the model output function in the linear data modeling score as the norm-based loss function, actually the evaluation will fail. And a potential explanation for this might be, in this case, the model output function cannot be well approximated by the linear models, which is an underlying assumption in the linear data modeling score methods. But by using the simplified loss function and the elbow loss function as the model output function in the linear data modeling score, we can find the interesting phenomena here. Yeah, so this is the main idea for the D-check methods. So basically, these two papers are just directly apply the check methods on the diffusion model, but based on different attribution targets. And we can also see there are some discussion space for these methods. Is there any question regarding the D-check methods or? Okay, then I will proceed to another type of methods here. So now I'm going to introduce another type of data attribution methods, which is I think is correlated with the influence function, but they are actually from another perspective. So in the previous methods, for the diffusion models, when we calculate the check methods, actually we need to compute the gradient for each gradients of the loss function for each training example and also for each test example. And actually, And actually, this can be very time consuming and also memory inefficient. Especially when we compare to the one-time inference, the computation of gradients is not that efficient. So in this paper, they propose a kind of hypothesis. They think that the train to last influence might be highly correlated with the test to train influence. So specifically, the train to test influence is just defined by the kind of leave one out arrow. So we train the model with the original training data sets, and for each test example or a group of test example, we just calculate the change of loss when applying the original models and the model trained without the specific training data points. And for the test to train influence, this is another idea, is that we actually first train a model with the training example and the test example we are interested in. And then we do an inference to calculate the loss function on the training data points, on the specific training data points we are going to attribute. And then we compare the loss change between the model that trained with that test sample and the model that trained without that test sample, or on the specific training example. So they think that these two influence actually can be highly correlated, and they did some empirical examination in the paper. Like for logistic model and convolutional neural network, they can observe high correlations in their empirical experiments. And also, if we want to explain this based on the influence functions, this actually can hold for influence functions. So for the train to test influence, which we are very familiar with, we can just write out the leave one out loss, approximate leave one out loss by this gradient terms. And then for the test to train influence, actually we just need to kind of upweight the specific test example in the loss function. And by some derivation, we can derive these terms using the same idea, same Taylor expansion idea. And in this case, because this Hessian matrix is a symmetric matrix, so we know that in the influence function, the train to test influence is actually identical with the test to train influence. Yeah. So based on this idea, they propose an algorithm, which is called a forward influence algorithm. So in this case, actually, when we try to attribute when we try to calculate the attribute.
Hello. Yeah, I'm not sure if it's my internet issue or.
Right. I think we lost Jingyan.
Oh,
Oh, okay.
sorry. Can you hear me now?
Yeah, I can hear you now. Yeah.
We can hear you now.
Okay, sorry. Probably internet issue.
Yeah.
Yeah, so let me just proceed. So the basic idea here is like we can
Oh,
use.
Jingyan, by the way, I don't see your screen right now.
Oh, sorry.
You probably want to reshare it.
Sorry about that.
First.
Okay. Oh, okay. Can you see my screen now?
Yes.
Okay. So the basic idea here is like we can just do a continual training to get the difference of this loss. And because for all the training, for all the test example, we can just do we can just train kind of train a model for once. We can just train the model once, so this can be more efficient than the train to test inference calculation. So that's the basic idea. Actually, it's very straightforward, and they proposed an algorithm for the like this. So basically, given a training data sets and the target test example, we just do a kind of continual training, and they use the gradient ascent here to help us get the model trained with the specific test example we are interested in. And then we just can do 2 forward paths to get the loss function and calculate the difference of the loss function to get an attribution score for the training data sets, for the training data points. So this is the basic idea. And this paper that actually used the unlearning methods to attribute the image generation task, I think is very similar to the idea they proposed in the previous paper. So they also defined the data attribution score as the difference of loss based on 2 different models. So the first model, they kind of unlearning actually is the same idea as the continual training above. They unlearn the specific test example we are interested in and calculate the loss function for each training example. And then they calculate the change of loss based on these 2 different models and define this as the data attribution score. And specifically, the difference here is that when they do the unlearning process, remember in the previous algorithm, they just do the gradient descent, use the gradients on the test example. But here they use another type of loss function and add kind of regularization term to avoid the catastrophic forgetting for the other training data sets. So basically, if we just directly do this gradient descent, use the gradient on the test sample, it might cause some problem for other training examples. The model might forget some information for other training example. So here they just add this term to avoid this happen. And then in this case,
So Jingyan, here F is the Hessian?
Oh no, F is not Hessian. So F is the Fisher information matrix.
And the loss is log likelihood?
Yes, in the diffusion model, they just use the negative log likelihood function.
Okay, so that's the Hessian, I think.
Yes, they are actually the same.
So why this approximation holds? I still don't see how it go from the first line to the second line. So they're just removing all the constant term and the first order term.
You mean from the first line to the
Yeah,
second
well,
line,
first
right?
line to the second. Yeah.
Yes, they first do the second order expansion, and because they think so for the first order term, because this model are not.
Oh, it's optimal. Okay.
Yes,
Oh,
so
I see.
it cancel out. Yeah, so
Thank
it takes it at 0. Yes,
Mm.
and they only retain the second order term here, and the F is the Fisher information matrix. So basically, the only difference here is just at this term, and in the gradient ascent, we will use we will have this kind of Fisher information matrix to do the gradient ascent, and then this actually has some relation with the influence function we've mentioned above. So in this case, if we write out the model parameters that train without the specific test example, it will just be the original model parameter and add one step updates based on this gradient descent methods. And in this case, consider the loss function on the specific training example, given the new model parameters. If we do the first order expansion, we can, oh, sorry, not first order expansion. If we just insert this term here, and yeah, and do the expansion, we can see, yeah, we can know that this loss function can finally be represented as the loss function on the training examples with the model parameters, and add one more term based on the gradients. And this term is actually identical with what we've got from the influence function. So finally, the data attribution score are related to the influence function methods. Yeah, so this is the idea for these methods. And the benefits here for this method is that, as we mentioned above, we can just do a quick unlearning and use the forward pass to help us gather this data attribution score, which might be more efficient than calculating the gradients when we apply the influence function based methods. And here are the experiments results. And we can see, I think the takeaway here is, so first, this type of unlearning methods can outperform the track-based methods. And I think the probably reason is that when they do the unlearning, although in theoretical justification, they just consider one-step update, but actually when they do the unlearning, this can be multiple steps, and the difference could be more significant. So probably this is a reason why they outperform the influence function-based method. It's not kind of infinitesimal effect. And also we can see in this figure, actually some image retrieval-based methods, which just calculate the similarity score in the predefined featured image, can be a strong baseline compared to the influence function-based methods. And yeah, and so for the, yeah, so this is their experiment, counterfactual evaluation experiment results.
Can I ask a quick question? So this is a loss change on which samples? So is this a loss change on the target? I mean the generated.
Yes.
It is Z hat, right?
Yes, the Z hat, yes.
Okay.
So the counterfactual evaluation here is just, so first they have a specific data sets with, that is the generated image, and which is the Z hat above. And they just calculate the loss change here. After remove, so they train a model from scratch by removing those attributed image, and they just calculate the loss change here.
Okay.
Yeah, and then they also did another evaluation based on the customized model benchmark, which I will go over which I will go over later. So the basic takeaway here is that they perform very well on this benchmark compared with the other image retrieval based method, but I will go back to this later. Yeah, so these are the data attribution methods we are going to talk about today. Is there any question? If not, I will proceed. Okay, yeah. So yeah, so the final topic we're going to talk about is the evaluation methods for the data attribution methods on image generation task. So first, basically there are two standard methods we've already seen in the previous slides. The first one is the counterfactual evaluation. And in the counterfactual evaluation, we given a trained data sets and the k-attributed image for a specific test image z hat we are interested in. We will train a model from scratch by removing those attributed image. And then we compute a loss change on the same synthesized image. Actually, I think they are just the same, use the same values, insert the same values in the loss function and calculate the change of loss. And the other, for the clip score or the L2 distance, actually they initialize the model with the same noise and then calculate the distance between the two generated images based with different models. So this is the counterfactual evaluation. And for the linear data modeling score, as we mentioned above, they just insert the loss function as the model output function to calculate the linear data modeling score. So the problem here is for these two methods, actually, it's very expensive to do the evaluation because both of them involve resampling and retraining of the model. So in this case, like in previous methods, usually they just evaluate the methods on some medium scale data sets. They cannot be very scalable to very large scale data sets like the line data sets, which are usually used in the diffusion model training. So in this case, Tier 1 methods propose a customized model benchmark. The idea is actually quite simple. They want to create some ground truths that computationally influenced by the exemplars, by some exemplars from the training data sets. So what they're trying to do here is summarized in this figure. So first, they start with a standard diffusion model, and which has been trained on the training data sets we are interested in. And then they will sample some exemplar from the original data sets. And after that, they do a fine-tuning specifically on this exemplar. They use the customized diffusion model here, which is a very efficient fine-tuning methods. So they can fine-tune the model very efficiently in a cheap way. And then we can get new models that can specifically generate some new images will computationally influenced by the specific exemplar. So for example, here, actually this model help us to insert this specific object, this animal, into each newly generated images. So given this specific customized model, if we just calculate the data attribution score on this model with a synthesized image as the query. So for example, we take this newly generated image here as the query, and we quantify the impact of the training examples on this specific image. We will expect that this specific exemplar will be the most influential, or at least very influential training examples, very positive training examples here. So in the evaluation, we can just calculate how the data attribution methods can help us retrieve this specific exemplar on this customized model. So this is their idea. So basically, they generated a kind of benchmark data sets based on this idea for the diffusion models, and then use this as a kind of evaluation method, evaluation benchmark. And also, this type of evaluation method actually motivate another type of data attribution methods, but I won't go over this in details here. So the idea here is actually instead of using the influence function-based method, a very straightforward idea to get the influential examples is directly compute the similarity scores between the test example and the training example. However, this might not be very effective in the general cases is that we usually use some out-of-the-box models to calculate the similarity scores. Like we can use the clip embedding or some other embedding from the self-supervised model to calculate the similarity score, but which can be which might not be very useful in the diffusion model, which are trained with some like different targets. So in this case, they propose a kind of methods to fine-tune the feature space based on their customized model benchmark. So they use some contrastive learning techniques to fine-tune the feature space. And then with that feature space, it might be helpful to do a general data attribution task. So this is a basic idea, but yeah, you can refer to the paper to get more details for these methods. And finally, I want to mention probably one limitation for this type of evaluation, because in this evaluation methods, they actually create specific data sets based on the customized model methods. And in the experiment, they want to examine that. So if one model performed well on this specific benchmark data sets, would that attribution methods also perform well on some general data attribution task? So in this figure, in the x-axis, this is the performance of these models. So here in this figure, each type of this point refer to a specific data attribution methods. Specifically, they just use the retrieval-based data attribution methods here. And the x-axis is the performance of the data attribution methods on their @1in benchmark, the customized model benchmark. And for the y-axis, they fine-tune the model with these data sets with different number of the training samples. So for example, here they fine-tune this model with 100 images from the training data sets, and they will expect that in the attribution process, because they are doing some fine-tuning in the attribution process, those 100 images could be the most influential images in the attribution process. So they use this to simulate a more general data attribution task. And this figure basically implies that although some methods perform very well on the customized model benchmark, like here, they actually do not have a very high the performance actually does not correlate very well with the general data attribution task. So which means that there are probably some gap between the attribution performance of the exemplar models and the assessment of the general attribution task.
Can I ask, like, so the y-axis basically is similar method, but you are just like now you're fine-tuning on a larger set of exemplars
Yes.
instead of like instead of just one exemplar.
Yeah.
And you're still doing retrieval, but you're just like basically having a higher required k, always higher k metric for the retrieval performance.
Yeah, that's true. Yeah, so this is for the customized model benchmark. And actually, these are all the methods we're going to talk about today. And if there's any questions, we can discuss now. Thanks.